So let's talk about what's going to be on your first unit exam. So we talked about two distances. The first distance is an astronomical unit, and it's the average distance between the Earth and the Sun. A light year is significantly farther than that, but we need that distance in astronomy. A light year is basically, here I have a star shining light at a person. If we were to locate the person and the star 1 light year away, then it would take energy from that light 1 year to travel to that person. So that's 1 light year. Then we talked about based upon the fact that light takes a certain amount of time to travel from point A to point B, as we look at a galaxy that is, for instance, your text says 7 billion light years away, then that we're looking at a star or a galaxy as it was 7 billion years ago. 12 billion light years away, that galaxy is as it was 12 billion years ago. And actually, that's kind of related to the next term. We kind of bump up against something called your cosmological horizon, which is you can't see past in light years when the universe was born. The next one, key dates and times on the cosmic calendar. So I thought this is pretty clever. Remember, this basically says, okay, the beginning of our universe, which is all the fabric of space and time and all the matter and energy that's in our universe now, when it unfolded, we set that as basically midnight, 12:01 on January 1st. And then go ahead, and where we are now is we are right at the cusp of the New Year. So we have a year to kind of condense all of history. And so these are key dates on the cosmic calendar you might want to add onto your note card. Hint, hint, I really like the rise of the dinosaurs. I think that's neat. December 26th. And then 4 days later, December 30th, the dinosaurs die. So the next one, at times it takes remember, all stars in our Milky Way galaxy are orbiting around the Milky Way galaxy. So we're orbiting around the center of the Milky Way galaxy. And the center of our galaxy actually is a supermassive black hole. And it takes 230 million years for the sun, where it is, to complete one orbit. There's actually two kind of questions balled up in the next one. Where is most of our galaxy's mass located? And actually it's located in the halo region. Remember, the halo is outside the disk. So it doesn't glow, but it's located there. And so actually that is dark matter. And then how did we determine that we have so much dark matter in the halo region of our galaxy? Actually, it was by observing the motion of stars. It kind of goes back to that 230 million years. It takes our star, the sun, to complete one orbit about the center of the center of our galaxy. We're doing that dance specifically related to where the mass in our galaxy is distributed. The next one is our universe is expanding, and kind of a classic is to relate our expanding universe to raisin bread. So here, actually, the raisins in raisin bread could be galaxies, or actually more likely clusters of galaxies. And we are a member of the local group, is our cluster of galaxies. And so actually, just as when you bake the raisin bread, the bread part gets larger and kind of carries along the raisins, so also as our universe is expanding, the fabric of space and time is expanding, kind of like the bread part in raisin bread, and it's carrying along our galaxies. Galactic recycling is actually why we have, on Earth, why we have anything heavier than hydrogen and helium. What happens within a galaxy is stars live their lives, and they die in an assortment of ways, and we'll be talking more about that later. But they leave their gases and dust for new stars to be born. And actually, as they live their lives, they manufacture heavier and heavier elements. So the next one, continue on this one. For new stars to be born. Ecliptic plane, okay, kind of looks like this, where, of course, you see the sun and the Earth orbiting the sun. the Earth's axis of rotation is tilted 23.5 degrees. I like this figure for that too. But what I've circled is the ecliptic plane, and so that's kind of like the sheet of paper that contains the plane that has both Earth's orbit and the sun. So last is we talked about we are always in motion, and so of course the Earth spins on its axis of rotation. The Earth orbits the sun. The sun itself is, like we said a minute ago in review, the sun itself is moving because it is orbiting the supermassive black hole in the center of our galaxy. And then the sun is moving amongst its fellow stars, kind of in the neighborhood. And then actually the Milky Way galaxy is moving amongst our galaxies, and the Milky Way galaxy is also moving because of the expanding universe. So on to Chapter 2. In Chapter 2, starting with circumpolar stars. Circumpolar stars are stars that never set below the horizon. So actually, circumpolar stars you're going to see as kind of a bullseye in the northern hemisphere around the star Polaris. If you were to do like a star trail, they would make a circle. And they will never set below the horizon. They never rise, they never set. Polaris, actually, in the northern hemisphere, we get to have a star that our axis of rotation is pointed towards, and that's Polaris. So also is that, so as the Earth orbits the sun, its tilted axis of rotation, the North Pole is always pointed towards Polaris. Okay, and I brought in a figure for the next one. If you're taking this class to be able to kind of orient yourself to the nighttime sky, I hope that works for you this semester. It's going to take a little bit of practice. So one of the things, an asterism, remember that's a subset of a constellation, but asterisms, or the asterism, the Big Dipper, which is part of the constellation Ursa Major, can be used to find the North Star or Polaris. So what you do is you use the far bowl stars, pair of bowl stars in the Big Dipper to point up to Polaris. They're called pointer stars, the far bowl stars in the Big Dipper. The next one, location of the North Star Polaris and your latitude. Remember we've talked about altitude in this class, that actually altitude is you can extend your hand in like the like from knuckle to knuckle, that actually is 10 degrees. If you extend your palm from tip of pinky to tip of thumb, that's 20 degrees. So actually you can use that convention to see what altitude Polaris is with your particular location. And the altitude then is the latitude of your location. Seasons and why they occur. Basically, we wouldn't have seasons if the Earth's axis of rotation were not tilted 23.5 degrees or having some tilt. I guess the bigger the tilt, the more exaggerated the seasons. But this has consequences on an assortment of reasons, or a certain assortment of consequences. One is that we know as we go through from January back to December, we know that we have different number of daylight hours. We have our shortest days in December and our longest days in June. So that actually changes the amount of solar radiation we get in a given day. The other thing is that in December the sun is lower on the horizon, and in June the sun is higher in the sky. So that higher angle, for instance, in June that the sun makes with the horizon, that has the consequence of giving us more direct sunlight. And with more direct sunlight, we have more intense rays and less depletion as the sun goes through the Earth's atmosphere. So why do we see only one side of the moon? And actually that's because of something called synchronous rotation. So synchronous rotation is the fact that in 29.5 days, the moon will not only go about or orbit the Earth, but the moon will also spin on its axis of rotation. Okay, so 29.5 days is both its rotation and its orbital period. And so because of that, like this young gal in this figure is showing you, we only see one side of the moon. The other thing is, so I brought in a picture from left to right, the photo of the moon. The left one is the near side of the moon, and the right one, the pocked one, is the far side of the moon. Terminator. relatively straightforward. Whenever you see we're looking up at the moon and you see the region that separates the side that you see that's reflecting the sunlight and the side that you don't see that isn't getting sunlight, that is called the terminator. Lunar and solar eclipses, why they occur. A lunar eclipse can only occur potentially when the moon is in its full phase. A solar eclipse can only occur when the moon is in its new phase. And so when a lunar eclipse occurs, that's when the moon is scooting through the Earth's shadow, particularly, hopefully, the umbral part of the Earth's shadow. And a solar eclipse is when the moon is casting a shadow on the Earth, blocking out the sun. So we have an assortment of types. Oops. There we go. We have an assortment of types. Okay. Down here on the left, I show you the lunar eclipses, and that we have a total lunar eclipse, a partial lunar eclipse, and a penumbral lunar eclipse. With regard to solar eclipses, we have a total solar eclipse, a partial solar eclipse, and an annular solar eclipse. Precession is that where the Earth's tilted axis of rotation remains tilted, but it kind of swings around and makes a cone. So there's a figure from your textbook about that. And actually, this has the consequence of making the Polaris hasn't always and will not always be our North Pole star. So the next one, hypothesis. I think I kind of got this. I think hypothesis actually is in chapter 3, but we'll go ahead and mention what it is here. Of course, hypothesis is a term used in the scientific method. Specifically, it is it's early on or earlier on where you have sometimes called a best guess to explain your observations, and hypotheses can be elevated to a theory. And I see I already threw up the other two terms there. Zenith is the point in your local sky that's directly overhead. It makes a 90-degree angle with the horizon. That's your zenith. And then just in general, local sky, I kind of showed that figure from your textbook. We have the term altitude. We talked about the altitude of Polaris is the latitude you are on the Earth. So that's where you can kind of extend your arm and get a sense for the angle above the horizon that an object is. That's the altitude. On to chapter 3. And somewhat obscure, I will grant you, is this photo from your textbook relating a sun dagger. So the sun dagger actually, and there are many man-made and natural sort of cool things like this, that the sun dagger on the summer solstice will have the shaft of light will pierce the center of the dagger, or the shaft of light acts like a dagger, and it will go through the center of the kind of concentric circles. Okay. Eratosthenes estimated the size of the Earth. Okay, and I thought this was pretty darn cool. Basically, he had he looked at shadows being cast for two locations at the same time. Now, he knew the distance between those two locations. One location, the sun was at the zenith, and the other location, the sun cast a shadow that was 7 degrees. And so actually he could use that angle, the 7 degrees, and the distance between the 2 points to estimate the diameter of the Earth. Was that not cool or what? The next one is Ptolemy, and Ptolemy was before the Copernicus revolution. So Copernicus was kind of finally back to putting Earth in the center Copernicus was back to putting the sun, thank you, in the center of the motion of the planets, but Ptolemy still had the Earth in the center of everything. So the sun orbited the Earth, the stars orbited the Earth, the moon does orbit the Earth, but the planets orbit the Earth. Now, one of the things that's called a geocentric model. One of the things that the geocentric model can't explain is why do the planets appear to go backwards, called retrograde motion, for a certain period of time. And so my point here is that Ptolemy introduced these things called epicycles, and you might need to, this is a small figure on this review page, but in your textbook you can pull it up. And epicycles were those kind of where the planet does a loop-de-loop as the planet is orbiting the Earth. Strange, I know. So the next term kind of goes along with that. So apparent retrograde motion is when the planet it appears to go backward in the nighttime sky. I believe that's westward. Direct motion is eastward against the background stars. So this backward motion actually occurs as a planet passes another planet, as both planets are orbiting the sun. And one of the things we learn actually coming up with Kepler's 3 laws is Kepler said that the closer the planet is, the faster it completes one orbit about the sun. That's his 3rd law. Major contributions of Copernicus, Brahe, Kepler, and Galileo. And actually I put them in order of when we talked about them in class and when they occurred. Copernicus, one of his students was Brahe. Brahe hired Kepler, and Galileo was kind of on his own. But you can see that Copernicus started what we call the Copernicus revolution, which is back to the heliocentric or sun-centered model of why the Earth and the planets do their thing. Brahe was a great observer. He had an awesome toys to deal with. Brahe did not use a telescope, but looked at the position of stars and planets. And Brahe actually observed a supernova. And Brahe also observed comets moving in the nighttime sky, night after night. Kepler, actually, he finally then came up with 3 laws of motion about how the planets move. And so actually Copernicus, Brahe, and Kepler, not so surprising, were all part of the revolution where we're going to put the sun back in the center of the planets orbiting the sun. So Kepler's 3 laws of motion, you can see down below. Kepler's first law simply described the shape of the orbits of the planets as not being circular, but being more oval. Specifically, that oval is called an ellipse, and this was a big, hairy deal. So that was a humongous breakthrough for Kepler. Kepler's second law then says that actually planets will move fastest when they're near perihelion, and there's a term coming up, perihelion. That's when the planet is closest to the sun. Oh, that's the next term. Perihelion is when the planet is closest to the sun. Aphelion is when the planet is furthest from the sun. So planets move fastest when they're closest to the sun, and when they're far out from the sun, they move slower. And actually, this is consistent with Newton's laws of just general motion coming up. Kepler's 3rd law says that the closer the planet is to the sun, the faster it will complete the faster it moves about the sun as it orbits the sun. And again, this is consistent with Newton's general laws of motion. So Galileo, the last one up there, actually I have something coming up. It says see below with regard to Galileo's contributions to solidify this heliocentric or sun-centered model. So Occam's razor. Actually, Occam's razor is a characteristic of you're on the right track for your hypothesis and or theory. So according to Occam's razor, and that Occam's razor says the simplest the model, the best. The simpler the model, the more it's more likely to be the real deal. So if you're familiar with the KISS principle, means keep it simple, stupid. Sorry, but that's actually Occam's razor. Hypothesis, then, I think we talked about a minute ago, is basically you are using the scientific method, and based upon observations, you say, well, this is my best guess. It's more than a guess, but based upon what I see, this is what I believe to be the situation. That's your hypothesis. And hopefully your hypothesis, after extensive experimentation, can be kinged to become a theory. So last term here is Galileo and his contributions. So he observed blemishes on the sun and the moon, that being sunspots on the sun and craters on the moon. He also observed objects orbiting the planets. So, for instance, he saw 4 large moons orbiting Jupiter, and we call those the Galilean moons. Galileo also saw, through his telescope, that Venus goes through phases. So, and that makes sense only if Venus is an inner planet orbiting the sun. So sometimes Venus is a crescent, sometimes it's a gibbous, sometimes it's full, sometimes it's new. So that makes sense if it is orbiting the sun. And also, Galileo used his telescope to look at that sort of milky-looking band that looked like fog, right? So he looked through at the Milky Way through his telescope, and he could see that actually what looked just like haze was little tiny stars. So he said, dude, since those are little tiny stars, they're so small because they're so far from us. So one of the things then, it got back to parallax. If those stars are so far from us, then you know what? We wouldn't expect to see parallax as excuse me, as the Earth orbits the sun and changes its position.